Okay, guys, we're going to start 8-3 today. We're going to make it two parts. The two parts are the integral test and P series. That's P series. And the integral test is up first. So just to refresh your memory, here's where we stand. We are in the process of sorting out infinite series into one of two sides. If they if the terms in them approach zero, then they're allowed in this bubble. And once we know the terms approach zero, we need to decide, do those terms that approach zero add up to a finite amount, or do those terms that approach zero add up to an infinite amount? And we've seen some examples of both with the geometric and with telescoping. But today you're going to get a new type of test, and with each section up through section 8.6, which is where we're going to cut this chapter off and have a test, by the way, you're learning a different test which helps you sort out which side of the bubble does my series go on. Keep in mind they're all ones whose terms go to zero, but some of those add up to finite and some of those add up to infinite. Okay, so the integral test works like this. Basically, you're going to turn your formula for your series into a function. Series or sequences are just functions where we only plug in the whole numbers. So the sequence version would look like this, and the function version would look like this. We would integrate that function from 1 to infinity. So it's just treating it, instead of treating it like a sequence, a list of terms, we're going to include all of the other terms. And our connection is basically this. If we plug in 1, I guess in this case we'd be plugging in 2. One thing you'll learn about infinite series and convergence is no term or handful of terms can affect it. If it's going to go to infinity, then one term can't stop it from going to infinity. And if it's going to converge to a certain sum, no term can stop it. It'll converge to a different sum if you throw that one extra term in there. But one or two or three terms isn't going to change the convergence or divergence. So let's say that this function, f of x, at its area from 1 to infinity is finite. Or let me just say that it converges. Let's say the integral from 1 to infinity of f of x converges, which means that the area underneath the black curve from 1 to infinity adds up to a finite amount. This is what we were doing in that one section in chapter 7 on improper integrals. Well, if I know that that area underneath the black curve converges, then it makes a lot of sense that the terms of the sequence would also converge. Because if I plug in 2, I get this value out of my function, but the term would be that much times 1, so I'd get this much area. So this is term 1. Technically it's term 2. Term 1 isn't going to change my outcome. Here's term 2. Here's term 3. So if the integral converges, then the series is going to converge also. On the other hand, let's say that f of x diverges, and we make it out of term 1 and term 2 and term 3 and term 4. If this function diverges, meaning that the integral is infinite, it diverges, then the series is going to diverge also. So this section is as simple as turning your formula for your sequence terms into a function and then integrating that function with an improper integral from 1 to infinity and just comparing the two. If your integral converges, then your series converges. If your interval diverges, then your integral diverges and your series diverges. One technicality here is f of x must be positive, continuous, and decreasing once you get to 1. Or technically you could start at 2 or 3 or 4, but by definition we start at 1. That just means that your graphs look like these general pictures. You're going to have a smooth, downward, swooping graph towards the asymptote of the x-axis. If anything else is going on, if there are discontinuities, that voids this test from working. Okay? So I'm going to give you an example, one of each, one of convergence and one of divergence. If you use the integral test, you need to say this red statement as part of your justification. It's just a technicality, but as far as preparing for AP, say that f of x is positive, continuous, and decreasing, and that way you know that the integral test applies. Okay, so our first example is going to be the sum from 1 to infinity of n over n squared plus 3. So this is the series form. We're going to turn that into a function just because when you integrate you deal with f of x instead of n's. So we're just going to call it x over x squared plus 3. Okay? Which is positive, continuous, and decreasing for x greater than or equal to, technically this one is at 2, and the examples in the book might ask you to prove these things, but as far as I'm concerned right now, if you just look at this function, you should know it's positive because we're talking about positive values of x. So the top's positive and x squared plus 3 is always positive. It's continuous because there are no asymptotes, really. There's nothing weird going on with the graph. And it's decreasing because as x increases, the bottom will always be increasing faster than the top. The quadratic on the bottom dominates the linear on the top, according to the hierarchy of domination that we've talked about previously. So those technicalities out of the way, the only thing left to do is to integrate this function from 1 to infinity and see what we get. Okay, either this is an integral that converges, in which case the series would also converge, or it diverges, in which case the series would also diverge. And we're just sorting out which of those two it is. This is called the integral test. Okay, I'm also going to give you a break. In Chapter 7, I would have made you do this. And on like that. I'm going to let you not do that starting now. Keep in mind that you should, if this were to come up on the AP test, but it's our focus now is series, so we'll just leave the infinity there, even though it can't really be there. All right, so how do we integrate x over x squared plus 3? The integral of x over x squared plus 3 is going to be, let's let u be the bottom, then du will be 2x. I almost have that. I need a 2 and a 1/2 to compensate for it. So then my integral is going to be a half of natural log of x squared plus 3. Parentheses instead of absolute values because x squared plus 3 is always positive. And I'm going to evaluate this at infinity and at 1. So I get half of natural log of infinity minus half of natural log of 4. And natural log of infinity is infinity. half log of 4 is some number. I don't really care what that number is right now. Infinity minus that number equals infinity. All right, log of infinity is infinity. It gets there really slow, but log of infinity is in fact infinity. Okay, so long story short, this integral diverges. It adds up to infinity. Therefore, my series is going to diverge as well. So my statement would be, since the integral from 1 to infinity of x over x squared plus 3 diverges, the sum from 1 to infinity of n over n squared plus 3 diverges also. So that's my final answer, divergence because of the integral test. Now, it makes a lot of sense if you think of the picture. This graph, I don't know the exact, I could graph it on my calculator, but this graph looks like this, as they all will in this section. And if it adds up to infinity, then my terms that are made out of the values from this graph will also add up to infinity. Okay, so another example. The sum from 2 to infinity of 1 over n squared of n squared minus 1. You'll notice sometimes we have to adjust our limits here. You can't plug 1 into this because you would get 0 on the bottom. So if you have to start at 2, start at 2. And that adjustment is not going to affect convergence in the least bit. All right, so let's add this one up. Basically, we're just going to make a function out of it and integrate from 2 to infinity 1 over x square root of x squared minus 1. I chose this one specifically because it's an integral that you should know but we don't use all the time. That integral fits perfectly into the model for arcsecant of x. So that'll just be a good reminder. I'll try to do those whenever possible. We're going to plug in infinity in 2. And we're not going to have to do the limit as b goes to infinity deal in this chapter, like I said before. So now all that's left is to figure out what's the arcsecant of infinity and what's the arcsecant of 2. All right, so arcsecant of infinity is saying where is the secant equal to infinity. I'm going to put some detail here because this can be a tricky question. Where does secant equal infinity? Which is like saying where does 1 over cosine equal infinity? Well, that's going to be the case when cosine equals 0, because 1 over 0, or when we approach 1 over 0, that goes to infinity. So cosine is 0, the x value is 0 when you get up to the top of the unit circle, and therefore, by that reasoning, the arcsecant of infinity is pi over 2. Right, if you remember your graph of secant, there would be an asymptote at pi over 2. And then we have the arcsecant of 2. So that's saying where is secant 2, which is saying where is cosine a half, and cosine is a half at pi over 3. So we've got some good quality unit circle reviews going on within this question. Pi over 2 minus pi over 3 is something. Is that pi over 6? All right. One final important aspect. My conclusion, therefore, the sum from 2 to infinity of 1 over n square root of n squared minus 1 converges. Pay attention to this last bit. You cannot conclude that the sum of the terms in the sequence is pi over 6. The integral converges to pi over 6. The series converges to something, but not necessarily pi over 6. This pi over 6. This is some number, but not necessarily pi over 6. So your conclusion is that your series converges because your integral converged, but not necessarily to pi over 6. So don't say the sum of my series is pi over 6. Are there two S's in necessarily? Are there two S's in necessarily? I'm going to have to pause for a spelling check. I can't write this if it's wrong. Okay, thank you. I've confirmed the spelling is correct, so I can move on. So our series converges because the integral went to pi over 6, but my series doesn't necessarily add up to pi over 6. If you remember, the ones that we can actually add up are down here. Geometric and telescoping. Integral test is not part of that. All right, so we have figured out how to sort out one side or the other. If the terms go to 0 and the integral converges, the series converges. If the integral diverges, the series diverges. All right, so we will call that part 1. We will do the p-series next, which is still part of section 8.3, but that's the integral test, so Young is out.